Black hole. Many people say that the black hole is the limit of human understanding. True to its name, black holes are always dark, eerie, and terrifyingly mysterious. Today, black holes are one of the key objects of observation for humans beyond the universe. But did you know that it wasn't until 2019 that humans truly obtained the first image of this black hole? Before this image emerged, black holes only existed in theories or complex physical equations of humans. But after the historic moment when the image was released, everything became clear. Black holes truly exist, and everything people have said about them so far is true. For us, black holes are both mysterious and terrifying objects, yet they contain the desire to understand the universe. So what do we know about them? How terrifying are they if humans were to face a black hole? Today, we will explore the most powerful monster in the universe and how we can survive when confronting it. Black holes, or singularities, are regions of spacetime where gravitational attraction is so strong that nothing, not even particles or electromagnetic radiation such as light, can escape from it. Einstein's theory of general relativity predicts that a sufficient amount of mass confined within a small enough space will deform space, creating a black hole. Surrounding the black hole is a boundary called the event horizon, where once matter crosses, it can never escape the black hole's gravitational pull. Black holes are called black because they absorb all radiation and matter that passes through the event horizon into their interiors, appearing as an absolute black object in dynamics. Based on the formation and characteristics of black holes, we can categorize them into three types: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes are those with a mass about 10 times that of the Sun, formed by the collapse of massive stars. This type of black hole is the most common, and many of these black holes have been discovered to date. Intermediate mass black holes lie between stellar mass black holes and supermassive black holes, with masses ranging from several thousand to 1 million times that of the Sun. However, there is still some debate among scientists about how such black holes are formed. Supermassive black holes are the heaviest black holes in the universe, with masses ranging from millions to billions of times that of the Sun. Scientists believe they may form through some special mechanism, such as the merger of massive star clusters, or when two or more black holes merge with each other. Although by definition black holes are completely invisible, their existence can be inferred through their interaction with the surrounding matter environment and light radiation. The matter falling into the black hole forms an accretion disk, where collisions and friction among particles result in a plasma state emitting intense radiation, making the environment around the black hole one of the brightest objects in the universe. If a star orbits a black hole, astronomers can deduce the mass of the black hole and its distance by studying the shape and orbital period of the star's trajectory. This data helps them distinguish whether an ultradense celestial body is a black hole or a neutron star. In this way, Many black holes have been discovered within binary star systems, and at the center of the Milky Way, there is a supermassive black hole with a mass approximately 4.3 million times that of the Sun. One common misconception is that black holes are extremely dense objects, as mentioned earlier. While black holes are formed from extremely dense matter, the black holes themselves are essentially nothing. Our Sun has a diameter of about 1.5 million kilometers, but if we were to compress it down to a smaller size, smaller and smaller until it turns into a sphere with a diameter of only about 6 kilometers and an immense mass. At that point, the Sun would continue to collapse and eventually disappear, with no surface or matter remaining to define it. All that would be left is an empty void of space. If you were to approach a black hole, you might not even realize that something terrifying is looming nearby. Imagine you're on a journey through space to venture into and explore a black hole. How do you think that journey would unfold? And could you survive and escape from it? To explain this, we need to take a moment to understand what curved spacetime inside a black hole is. Since the 20th century, Einstein's equations describe how spacetime reacts to matter and energy. You can search for the keyword Einstein field equations to delve deeper into these equations. If you throw something around the Earth, you'll notice it follows a curved path. If you throw it fast enough, you can put it into orbit around the Earth. Then it will follow a perfect circular path. We have some examples like the International Space Station, ISS, for instance. It's launched with a speed of over 28,000 kilometers per hour on a curved path it's falling on, or more precisely, a perfect circular orbit around Earth. Its engines are off, and it's actually falling around our planet. The orbits of satellites or the International Space Station illustrate a shape for curved paths in space. So, if you're exploring space and don't realize you're encountering a black hole, you might be surprised to find yourself near one because there's no light escaping from around the black hole. A black hole acts like a lens. Therefore, light around the black hole is distorted by the curvature of spacetime, but instead of converging or dispersing light, it bends light infinitely. We'll explain this further when discussing the image of a black hole in the later section, returning to the journey. If you realize you're near a black hole, it's already too late. You're practically caught by it, and any attempts to struggle and escape would be futile. Even if you somehow manage to control your spacecraft to escape, the first thing you'll encounter is trouble. That's the material I'm carrying with me. Let me help you understand why. Through describing the difficulty of escaping Earth's gravity, you'll understand why. Do you know how much speed is needed for a spacecraft to reach orbit? Only when reaching a speed of 7.9 kilometers per second can an artificial satellite or spacecraft avoid falling back to Earth. Spacecraft bound for the Moon need a speed of 11.2 kilometers per second, and to travel to other planets, even greater speeds are required. How do we achieve that speed? Only rocket propulsion can handle it. To accelerate an object to a speed of 7.9 kilometers per second to escape Earth's gravity requires a tremendous amount of energy, equivalent to the energy needed to power 1,540 watt light bulbs for 1 hour. On the other hand, rockets achieve flight by expelling gas behind them to create thrust when expelled rapidly. The faster the rocket flies, and the greater the desired flight speed, the higher the demand for a high gas expulsion rate, requiring a significant amount of fuel to be carried. Let's say the gas expulsion speed is 4,000 meters per second. To achieve an escape velocity of 11.2 kilometers per second, the rocket would have to carry a fuel load several times its own weight. Now, imagine how immense the gravitational force a black hole would generate with a mass millions of times that of the Sun. Even if the spacecraft could withstand that gravitational force, where would you get the massive amount of fuel needed to achieve the necessary escape velocity? Once you're within the influence of a black hole, you won't be able to escape it at that moment. The answer to whether you could survive to escape a black hole is quite clear. There's simply no way when approaching a black hole. Not only is space curved, but time is as well. The time between heartbeats, between breaths, between streams of thought seems to slow down compared to someone far from the black hole. For yourself, the time-related experience remains entirely normal because you're synchronized with the time reference frame around the black hole. As you move closer to the region of infinitely curved spacetime, someone outside will see that your watch has completely stopped. But that's not all. After a while, if you can still survive, you'll cross a place called the event horizon. This is the area where nothing, not even light, can escape once it enters. Here, as you're being pulled towards the event horizon, you'll experience a special effect called spaghettification. It's easy to imagine. Anything that gets too close to a black hole will be stretched out like strands of spaghetti. The effect is caused by uneven gravitational forces distributed across the object. Imagine you're being pulled closer to the black hole with your feet pointing forward. The gravitational force will pull harder on your feet than on your head, causing you to be stretched out rather than squashed. Moreover, your limbs won't be attached to your body's center of mass anymore, but will be pulled in different directions. As a result, your body parts will elongate like they're made of elastic material. You can imagine it similar to the character Richard in the Fantastic Four, but at a much more horrifying level. It stretches, tears you apart, and your spacecraft until molecular dissolution into the void to the point where it's no longer ordinary matter. At this moment, you're essentially nothing, but let's continue hypothetically. assuming by some miraculous means you and your spacecraft manage to survive this region. What awaits you beyond? Objects that venture deeper into the black hole will face even harsher conditions. The center of the black hole, also known as the singularity, is a place that cannot be explained by our current understanding of physics. It's a place where density and gravity are infinite, yet the volume is infinitely small. Here, classical laws of physics no longer hold true, and the combination of quantum mechanics and general relativity becomes the sole theory explaining the nature of black holes. With such harsh environments and awe-inspiring scenery, matter falling into a black hole will no longer exist in our familiar universe. It may be completely lost or transformed into part of the black hole. We have no definite answers about the ultimate fate of matter. This only adds to the mystery of black holes, leading to many fascinating hypotheses. If you were to reach this singularity, you might recall the movie Interstellar from 2014. In that film, after being pulled into the black hole's blackness, the main character passes through the event horizon and drifts into the five-dimensional space. Inside the five-dimensional space created by gravity, all signals of light and sound cannot transmit outward. The concept of a five-dimensional space was proposed by the scientific advisor of the movie, a renowned theoretical physicist at the California Institute of Technology. This hypothesis is fascinating because it portrays a black hole as a cosmic photocopy machine. It suggests that black holes have another surface where everything isn't pulled deep inside but rather falls onto some surface. Think of anti-counterfeit stickers, where there's a real and a fake surface, and the surface of a black hole is similar. So, in this scenario, you might find yourself peacefully on a surface inside another dimension. However, this surface has all the conditions needed to describe a three-dimensional object. Hence, you would be deceived into not recognizing it's just an illusion. This means that who knows, right now, we might already be living inside a black hole. But things could go much further beyond your imagination. It's not just Earth, the entire universe could have been inside a black hole. This means that black holes might help us decipher the origin of the universe. Many have wondered what existed before the Big Bang, which initiated everything. We know that the Big Bang occurred approximately 13.7 billion years ago, merely 10 to 36 seconds after the big explosion. Space inflated like a ballooning ball. Before the Big Bang, some researchers suggest that the universe existed as a single, dense, and infinite point known as the singularity. This singularity then ruptured and has been expanding ever since. This is fundamentally opposite to the nature of a black hole, as a black hole is also an infinitely dense point in spacetime. However, instead of spewing out, expanding everything, it sucks everything in. However, if our universe is inside a black hole, continuously pulling matter from the outside in, it's clear that the inside part would be expanding. Could the formation of a black hole imply the creation of a new universe within it? At present, some opinions suggest that it's impossible for black holes to reach gargantuan sizes to contain entire universes within them. However, the largest black hole we've ever discovered, Ton 618, is of an unimaginable size, with an event horizon diameter of over 390 trillion kilometers, 43 times the diameter of our solar system. This size is too small to accommodate even a galaxy, let alone a universe. So how could the entire universe fit inside a black hole? Our universe is expanding rapidly to the extent that we can never reach its edge due to the curvature of spacetime. It's highly plausible that our universe has a shape akin to that of a donut. If you attempt to go beyond the edge of the universe, you would only end up circling around, and ultimately, your destination would be the same point from which you started. Just as you cannot reach the edge of the universe, you also cannot reach the center of a black hole. Therefore, if our universe exists within a black hole that exists within another universe, it means that reality consists of a collection of overlapping universes containing black holes, each carrying within it a universe. If indeed each black hole contains its own separate universe, then the true shape of the cosmic island is something like a tree branching out into different houses. The theory of a black hole universe may help us solve other physical problems. Specifically, it may help explain dark energy driving the expansion of the universe. No one knows what it truly is or why the universe not only continues to expand but also expands at an increasingly faster rate. So what would happen if this dark energy, originating from outside our universe, is drawn into the black holes, where the matter from outside turns into energy inside and accelerates our expansion process? This could also help explain the early and rapid expansion of the universe after the Big Bang. Although the theory of a black hole universe may answer some questions, it raises others. We don't know how matter from outside becomes energy inside. But assuming we can solve all these issues, how can we check if we are inside a black hole? That may require larger confirmations from scientists. Another interesting hypothesis about black holes is that we could use them for time travel, as mentioned at the beginning of the video. When space is stretched, time is also affected, and clocks near massive objects will run slower than clocks near much smaller objects. Clocks near a black hole will run much slower than clocks on Earth. 1 year near a black hole could be equivalent to 80 years on Earth, as you may have seen illustrated in the movie Interstellar. In this way, black holes could be used to travel to the future if you want to visit Earth's future. Just fly near a black hole and then return to Earth. If you get close enough to the black hole center, your clock will run slower. But you can still escape, as long as you don't cross the event horizon. Of course, this is theoretical because, as we've analyzed, no spacecraft at the current time has enough power and fuel to escape the influence of a black hole. But what about the past? This is where things get really interesting. A black hole bends time to the infinite. Imagine taking a piece of paper and connecting both ends to create a loop. That's what a black hole can do with time. This creates a natural time machine. If somehow you could enter the loop, you would find yourself traveling on a trajectory through space-time starting in the future and ending in the past. Inside the loop, You would also find that cause and effect become very difficult to explain. Things happening in the past create the future, and this in turn causes things to happen in the past. Suppose you were to find a black hole and you wanted to use a reliable spacecraft to go back and visit the dinosaurs. Firstly, you can only travel into the past of the black hole itself. That means if the black hole formed after the extinction of the dinosaurs, you wouldn't be able to go back to a time long before that. Secondly, you might have to surpass the event horizon to enter the loop. This means that to escape the loop at a specific time in the past, you would need to break free from the event horizon. You'd have to move faster than the speed of light, which is impossible, as we've mentioned many times. So, while it's fascinating to think about the time-bending properties of black holes, visiting the dinosaurs or traveling to the future remains just a fantasy for the foreseeable future. Although black holes are among the most enigmatic places in the universe, our understanding of them is still limited. Scientists are striving to study the nature and behavior of black holes in hopes of unveiling the secrets they conceal by observing the radiation around them and employing advanced simulation techniques. We may gain deeper insights into the harsh environment and astonishing phenomena that matter falling into black holes must face. However, the day we officially uncover the mysteries of black holes is unlikely to come anytime soon. You might find it hard to believe, but despite centuries of research on black holes, we only obtained our first image of a black hole a few years ago. Indeed, our history of studying black holes resembles a television series spanning centuries, and the first image of a black hole is the result of countless brilliant minds' efforts over hundreds of years. The concept of an object with such massive mass that light cannot escape from it was first introduced by this man in a letter to the renowned English physicist Henry Cavendish in 1783. He described that if the radius of a sphere with the same mass as the Sun were less than about 500 times the radius of the Sun, an object falling from an infinite distance toward it would achieve a velocity upon reaching the surface of the sphere greater than the speed of light, assuming light is affected by gravity with the same force proportional to its inertial mass. Like any other object, all light emitted from the surface of the sphere will return to it due to the gravitational pull of the sphere. In 1796, Pierre-Simon Laplace, a French mathematician and astronomer, also presented this idea in the first and second editions of his book outlining his system of the world. These hypothetical dark spheres were forgotten in the 19th century, as most physicists believed that light had no mass and could not be affected by gravitational forces. Thus, its being pulled back was deemed impossible. It seemed like everything would forever remain buried in the flow of science. However, one man appeared and changed everything: Albert Einstein. In 1915, Albert Einstein completed the general theory of relativity, in which he had previously predicted that gravity would bend the path of light. Just 2 months after announcing the theory, astronomer Karl Schwarzschild found the first accurate experimental test for Einstein's equations. The solution that Karl Schwarzschild found describes the gravitational field for a point mass and a sphere evenly distributed in four-dimensional spherical coordinates. Because this is a rather complex mathematical knowledge, if you are interested in the Schwarzschild solution, please search for more information from academic and authoritative mathematical sources. This solution also has a peculiar property known today as the Schwarzschild radius. At this radius, the time described by Schwarzschild coordinates becomes discontinuous. To put it more simply, the Schwarzschild radius of an object is the limiting radius, at which if the object's size equals this value, it will become a black hole. Many scientists thereafter actively researched and produced very promising results, but these findings marked the beginning of the golden age of general relativity. It marked the moment when general relativity and the physics of black holes became major research directions in modern physics. During this time, we also witnessed the discovery of pulsars, rapidly rotating neutron stars, in 1967. However, until then, physicists still regarded neutron stars as similar to black holes. The subsequent studies by Stephen William Hawking and many other prominent scientists in the early 1970s gave birth to the field of black hole thermodynamics. These laws describe the properties of black holes based on characteristics similar to those of thermodynamics, establishing relationships between mass and energy, event horizon area with entropy, along with surface gravity with temperature. In 1974, Hawking further solidified these connections by demonstrating that quantum field theory in curved spacetime predicts that black holes emit radiation proportional to their surface gravity. The term black hole was first mentioned by physicist John Archibald Wheeler in a lecture in 1967. After Wheeler popularized the term, it quickly became widely used by the scientific community and the public alike, marking the journey from conceptualization to the name of the black hole. It's been a long and tumultuous journey, but the quest to capture the first image of a black hole has been exponentially challenging. Let's take a look at this image we're seeing, which is the result of a collaboration between 8 observatories worldwide and over 200 leading astronomers, scientists involved in the Event Horizon Telescope (EHT) project, a global array of radio telescopes. The EHT project utilized 8 radio telescopes across the globe, creating a virtual Earth-sized telescope to capture images of the black hole. The image unveiled by researchers is of the black hole at the heart of the M87 galaxy, located in the Virgo supercluster about 55 million light-years away from Earth. This is the first actual image of a black hole in the universe. All previous images we had were products of imagination or computer simulations based on data and analysis by scientists. However, unlike the simulated images from before, the published image is not a swirling, majestic black sphere with giant swirls of cosmic material. The first image of M87 is just a strange, circular shape in yellow and orange. Why is that? Have we been imagining black holes incorrectly all along? Why isn't it beautiful? But we still imagine it, don't we? The only way to answer this question is that reality rarely lives up to the movies. Even this picture is the same. This is indeed an image of the black hole, but it is not a direct image of it. We can only see the shadow of the M87 black hole. Theoretically, a black hole in the universe is an invisible object. However, we can still see the outer edge of the black hole and the event horizon, but this will only happen under certain conditions. If a black hole appears within a bright region, such as a luminous gas disk, we can observe the black hole creating a dark region within it, similar to its own shadow. The M87 black hole, although not the closest to Earth, has the largest mass. It is considered the highest likelihood observation target for the project. In the image published by scientists, the black circular shape in the middle is merely the shadow of the cosmic black hole. Its boundary is delineated by luminous matter surrounding it. However, the color of the circle does not represent the true colors of the gas and dust surrounding the black hole. The yellow-orange hue in the image is a color chosen by EHT scientists to represent the brightness of the surrounding matter. Yellow signifies the highest brightness, red indicates lower brightness, while black symbolizes little to no brightness. If subjected to spectral analysis, the light from the ring surrounding the M87 black hole may very well appear white with hints of blue or red. Over time, as our understanding of black holes continues to advance, we can dream of a future where this cosmic monster is decoded. At that point, all hypotheses related to time, matter, event horizons, or the fifth dimension will surely be illuminated. What do you think about researching black holes? Is it worth our efforts, and could decoding them open a new chapter in the history of science? Thank you very much for listening and supporting. Please leave your thoughts in the comments section. Goodbye and see you in the next videos.